We continue with our 3-lecture sequence on structural systems reliability. In the previous lecture, we introduced the concepts and started looking at the series system. We started with the simplest possible configuration, a 2-unit load sharing system, and we studied the effect of dependence among those 2 unit strengths as well as uncertainty in the load that they share. As I mentioned, looking at series systems is not only instructive, but it's also very useful because many problems in structural systems reliability actually turn out to be series systems, if not physically, then at least logically. So with this lecture, we are going to look at one such situation where the logical arrangement of the system is a series. We have a very simple structural member, a cantilevered beam, and it has 3 failure modes. So the free end is C, where there is a point load P. W is the uniform distributed load, and we would like to look at bending failure, shear failure, and excessive deflection failure. Now, our knowledge of mechanics tells us that if bending failure has to occur, it is most likely to occur at the fixed support B, because that's where the highest bending moment occurs under this sort of load. And likewise, if shear failure has to occur, it will occur at B, where we have the maximum shear force. Again, and finally, if deflection has to be looked at, the largest deflection will occur at the free end C. So this way, we reduce the dimensionality of the problem considerably. Also, it's clear that now we are looking at a logical arrangement of 3 failure modes, which give rise to a series system, as we will see. First, let's look at bending failure. So the maximum applied bending moment comes simply from statics. It's PL plus WL squared by 2. The bending moment capacity, looking at plastic section modulus, is SZ times Y being the yield strength, and bending failure occurs when the applied moment exceeds the moment capacity. Coming to shear failure, the applied shear at point B is P plus WL. The shear force capacity is 0.6 times the area resisting shear times the yield strength, and shear failure occurs when the applied shear exceeds the capacity. For the excessive deflection, we do a linear elastic analysis, and the deflection at point C is WL to the power 4 over 8 EI, E being the Young's modulus and I being the moment of inertia, plus PL cubed over 3 EI. And we allow a maximum deflection of span over 165. Putting all of these 3 together, we have the union of 3 failure events, and that's why we call it a series system, because failure in any of these 3 modes, if any of these 3 limit states are exceeded, we have system failure. Now, we are going to solve this problem and see the results or learn some of the different aspects of it through plots and graphs. So we have chosen only 2 of these quantities to be random variables, the 2 loads. All the other quantities, the geometric quantities, the strength type quantities, we have for the time being left as non-random, but later on in the next example, we are actually going to look at all of them being random variables, and also we have some dependence among them. And the way that we have chosen these numbers for this particular problem is to just make sure all the limit states are captured nicely on one single graph. So this number 165 is actually a result of that. So let's now define all the numbers in the next slide. So let's first introduce the load variables. Let's say the point load P is Gumbel with mean 5 kip. That unit kip is missing, and the distributed load is 1 kip per linear foot with a COV of 20%, and let P and W be independent. Later on, we are going to consider dependence among them in the next example. The strength variables, for now, we have them as non-random. So the yield strength is 36 KSI and the stiffness is 29,000 KSI. So we are using non-SI units for this problem. Finally, the geometric variables, also non-random, as I said. The span length is 6 feet. The plastic section modulus is 20 cubic inch. The moment of inertia is 91 inch to the power 4. And the area resisting shear is 0.66 square inch. So with this now, let us display the problem graphically and study the limit states in the basic variable space. So with all these numbers, we can plot these 3 limit states on the space of P and W. So W is on the x-axis, normalized by its mean value, and P is on the y-axis, normalized by its mean value. And you see that we have plotted the 3 limit states, and clearly the limit states are linear in these 2 variables, whether it be shear or flexure or deflection. P and W appear just in their linear forms. So we have 3 linear limit states. The green one is flexure or bending, the red one is shear, and the blue one is deflection. Now, because this is a series system, that is how we have defined failure. A failure of the system is failure in any of these 3 modes. So we have the union of these 3 limit states, and the failure region, if we were to identify it on this PW space, it's going to look like this. So we have taken the union of the individual limit states. So you see in the left portion it's governed by deflection, in the middle portion it's governed by flexure, and in the lower right portion it's governed by shear. Obviously this sort of relationship would change depending on the changes in the geometric properties, changes in the allowable limits, and so on. So as I said, for the purpose of this graphical representation, the numbers were chosen so as to have all of these things kind of be in the same region, so that we could nicely see the effect of the system interaction. We also see that all these limit states kind of are dependent on each other, because their slopes are more or less in the same range, and we'll see what it means in the next few slides. So the next slides will have the map of the basic variable space onto the standard normal space. Why? Because we are going to now solve this problem using FORM. So now we are going to solve a system reliability problem with the help of first order reliability method, which we have already looked at in the context of component reliability. And we are going to use the simplest possible transform, the second moment transform, or the Haushofer-Lin transform, which means the distribution of P being Gumbel, for example, is not going to be used. We are just going to use the first 2 moments of that random variable. So let's do that, and we have done this many times in the context of component reliability. So this is what the 3 limit states look like transformed onto the standard normal space of u1, u2. So u1 and u2 are standard normal independent random variables. So the green is flexure, the red is shear, and the blue is deflection limit state. And if we again shade, this is what the system failure region would look like. So now we have three optimization problems at hand. Each of these limit states will have their own beta points and their own beta values. So let's go through that step by step. So the first one, the M1, the safety margin corresponding to bending or flexure, is, as we showed in the first slide on this problem, is given in terms of P and W, and P and W are now expressed in terms of the corresponding values of U1 and U2. So we end up with a linear equation in U1 and U2. As you see, it's 144 minus 43.2 U1 minus 54 U2. So just to check, at the origin, U1 and U2 are 0. We have M1 positive, so the origin is in the safe region. If we want to find the minimum distance point to this limit state, that's the arrow that you see. So that is the minimum distance point from the origin. Its length is beta, and its cosines are the sensitivities, which actually we are going to use later on. So the value for this flexure limit state, beta, is 2.08, and the optimal point is approximately 1.30 and 1.63 in terms of U1 and U2. The red line, the shear limit state, also we know its form once we transform P and W to U2 and U1. We get a linear limit state for M2, which is 3.256 minus 1.2 U1 minus 0.75 U2. And that's the minimum distance point with the red arrow that you see on the figure. And the value of beta for the red line is 2.30, and the optimal point is 1.95 and 1.22. And likewise, we could analyze the deflection limit state. Again, it's linear in U1 and U2, and we have seen the forms. Again, let's make sure that M3 is positive when U1 and U2 are 0, so the origin is in the safe region, just to make sure. And the linear form of M3 in terms of U1 and U2 are there at the last line of that blue block. And we can also locate its minimum distance point, which is that blue arrow that you see on the left, and the distance is 2.29, and the optimal point is 1.18 and 1.97. So this way, we actually have solved the three individual limit states for flexure, shear, and deflection. Now we need to combine them, and that is the new challenge which we have not solved yet. But what do we need now? We need to realize that this system failure probability, which is P of M1 less than 0 or M2 less than 0 or M3 less than 0, and M1 and M2 and M3, they're all normal random variables. We see their statistics. M1 is normal 144 mean, and 69.2 is the standard deviation. Likewise, M2 and M3, they are each normal, but they are dependent. They are dependent because each of them is a linear function of the same two variables, U1 and U2. So even though U1 and U2 are independent, M1, M2, and M3 are mutually dependent. So we need to find their dependence if we if we have to find P of FSIS. So we need their covariance matrix, and we also need to, as we know, to cast this required PFSys in terms of a joint CDF, because all the joint normal distribution values are presented in terms of joint CDFs, and as does MATLAB. So we need to somehow cast this as a problem of joint CDF, so we need intersection of events, not union of events. So let's see how we are going to do that. To do that, we need to go back to what we learned earlier in part A of this course, linear combination of random variables. Let's recall a vector of n jointly distributed random variables x, whose mean vector is mu x, mu1 up to mu n, whose covariance matrix is Vx, and n by n square matrix. If we make a linear transformation of this, y, a new vector whose size is m, given by a0 plus ax, a0 being a column vector of size m and a being a rectangular matrix of size m by n. So then we have a new random vector y, and its mean and covariance matrix we know is, as you see on the screen, the mean of y is given in terms of the mean of x, the covariance matrix of y is given in terms of that of x with the help of a0 and a. Now, in the special case that the x's are independent standard normal, so x is identical to u, then and if we give the name m to y, so then this m is a joint normal random variable, which is what we are trying to get at, and the mean and covariance matrix of m is now then going to look like the mean of m is that constant a naught, that vector, and the covariance matrix of m is simply a transpose, because the v of x is now the identity matrix. So we need to remember this, and with this knowledge we can go back to our cantilevered beam problem and derive the covariance matrix and the mean vector of m being m1, m2 and m3, the three safety margins. So these are the individual beta values. This is the system reliability. These are the m's. So after doing the computation, the covariance matrix of m is what you see on the screen, that the 3 by 3 symmetric matrix. And just for our information, just for our interest, although we don't need this for MATLAB, the correlation matrix looks like this, and it's quite interesting to see that all the failure modes are highly correlated. This is what I alluded to earlier, and that's because you see they are quite closely linked. They have their slopes around the same values, and the correlation coefficient is basically the cosine of the angle between the three minimum distance lines. So the cosine of the angle pairs between the blue, red and the green arrows actually are the correlation terms. So now we are in a position to solve this problem using MATLAB, the MVN-CDF command, provided we can express this problem as in terms of a normal CDF. So we needed the covariance matrix. We have done that. We now need to cast this PFSys in terms of a joint CDF. So we convert the union probability using De Morgan's law to intersection probability. So PFSys is now 1 minus P, M1 greater than equal to 0 and M2 greater than equal to 0 and M3 greater than equal to 0. So now we have intersecting events, so that's good, but they are of the greater than type, so we have to convert them to the less than type, so which is obvious. m1 greater than equal to 0 is minus m1 less than equal to 0. So we convert that. So now we have reached the desired form, except that we now have minus m1, minus m2 and minus m3, which should not be a problem because the mean of minus m is minus of the mean vector of m, and it doesn't matter whether it's plus or minus, the covariance matrix remains the same. So the PF6 is 1 minus the three-dimensional normal integration at 0 with the mean vector minus EM and the covariance matrix VM as we have already derived. So these are the two, the mean vector and the covariance matrix, and MATLAB gives us the value of 0.0207, which if we do the normal CDF inverse comes to about 2.04. So it's interesting to note that our system reliability is 2.04, which is obviously, as it should be, less than all the individual beta values, 2.08, 2.29 and 2.30. And we can also see that the failure mode that is most dominant governing is the bending mode, which is typically what we see for beams of this type. This brings us to a nice conclusion of this this system reliability problem of a single structural member. Now, if we have to generalize this and use FORM to solve this sort of series reliability problem, this is what it looks like. We have the union probability of m limit states, and that, as I said, could be given in terms of 1 minus a joint CDF, a joint normal CDF, and now we are using joint normal CDF with 0 mean and with unit variance. So standard normal CDF, that is phi subscript m, that is evaluated at beta. Beta are the individual element limit states, the individual gi less than 0, that, or gi equal to 0, that is the each of the betas, and R is the correlation matrix, not the covariance matrix, because we are talking about standard normal now. R is the correlation matrix, and if we have the means, either tables, formulas, or a software such as MATLAB, we can find the system failure probability, and from that the system reliability index.